Discussion here about least common denominators. Now this is something that you've talked about previously in other courses, 7th grade, 8th grade math. And at that time, maybe we didn't think it was really all that important, okay? But now we get to a stage where we're actually going to need that to conduct further algebra. And that's the idea, is that every time that we learn something previously, there was a purpose for it. If there wasn't a purpose for it, it wouldn't be something that we covered. Does that make sense? Okay. Even though that you might think outside of school, a lot of this stuff isn't maybe necessary, the things that we learn in these individual courses are designed to then be used in the next course. If we take that approach and understand that that's going to be the case, then when we're learning something in this course, and right now we're learning how to solve equations. If we take equations seriously, it's going to pay off huge dividends for us down the road because they are used in almost every single class and section and chapter beyond what we're working on, okay? And the faster we can learn how to solve equations, the obviously quicker we set ourselves up for success. So going back and talking about least common denominator, the idea of a least common denominator, I'm just going to give you the procedure here for doing this. You're going to take and factor each fraction's denominator down to all prime numbers. Okay? No matter what number you start with, you can break it down through division so that you're left with a product of prime numbers. Okay? All your factors will be prime. So, for instance, we could take the number 20. Okay? And if I divide 20 by 2, that would give me 2 and 10, right? But what's 10 divided by? 2 again, it would give me 2 and 5. Okay? Each one of these is a prime number. 2 times 2 times 5 gives me 20. Does that make sense? Okay? Now, the way we would usually write that, we'd write it as 2 squared times 5. But if I did maybe, let's go like 144. Okay? Well, that would be 2 times 72, but 72 is composite, meaning it's not prime. So what can I divide 72 by? Okay, 9. So I get, this would be 2 times 9 times 8, right? That's what 72 is. What can I multiply together to get 9? 3 and 3, right? So this could be 2 times 3 times 3 times 8. But what can I multiply together to give me 8? 2 times 4? But doesn't that 4 turn into 2 times 2? Okay, so here's the prime factorization of 144. If I take 2 times 3 times 3 times 2 times 2 times 2, I will get 144. Now the best way for us to write that would be 2, there's 4 of them, so I write it to the 4th power, times 3, and there's 2 of those, so I write it as 3 squared. So we'll do that. So those are little examples of how we factor into prime numbers. Okay? You will then create your LCD by choosing factors that are represented in all denominators. I'm not sure if we should maybe write this way. We say we make sure that each factor is represented. meaning we've got to use each factor, okay? Now, the idea of that, or the point of that means if a factor that repeats, choose the one with largest exponent. So if I had, if I was trying to find the LCD between 20 and 144, okay, you see that 20 has a 2 squared in it, right? But 144 has a 2 to the 4th in it. They both have the same 2 as a factor, right? We would choose the 2 to the 4th because of the power being bigger than 2 squared. Okay, and that 2 to the 4th would become part of my LCD. Okay? If I wanted to then continue to find the LCD between 20 and 144, okay, so let's just kind of continue with that example. So we would look at this and say, okay, well, a 2 needs to be incorporated. But because this is a 2 squared and that's a 2 to the 4th, we'll use the 1 with the 4. Okay? Then we go to the next factor. There's a 5. 5 needs to be represented, so I'll put 5 in here. Okay? So that would look at all those factors, right? Now I need to come down here, and there's still factors that need to be left over, right? A 3 is here. So I need to incorporate 3 squared. So if I go through and multiply that out, I don't have a calculator open. Let's go. So 2 to the 4th is 16. 16 times 5 is 80. And then 80 times 9, 720, right? Okay. So that's 720. So that is the least common denominator. And what that really means, guys, is that is the smallest number. Okay, so if I start multiplying 20 and 144, okay, the first time that they are going to be, and I start multiplying them, the first time that they are going to become the same number is when we reach 720. Does that make sense? So basically what that means is I can make 20 and 144 both grow into 720. Okay? Let's see if we can, I don't know if I got a way of doing this. We can do this with Excel. Let's see here. All right, so if I take, I always say 20 and 144. Okay, then I'm going to go 40 and 288. Now, the nice thing about Excel, and I'll zoom in on this so you guys can see it a little bit better. View to selection, there you go. I can get this thing to kind of show the pattern. So it just kept adding 20. Does that make sense? Okay. And then here, do the same thing. Okay. And basically what I want to do is I want to go through here and say, okay, when do they become the same? Well, they're never both going to be anything under 140, right? So I'm going to cut those out. I just can't do it that way. Both of them are going to be, this one's no way, this one's going to be under 140. So keep looking here, and then comparing that list over here. When's the first time that I see a number over here show up in this list over here? And that first time that happens is all the way down here when I get to 720, right there. That's the first time that I see a number over here show up. Does that make sense, everybody? Okay. So that's kind of what we're doing when we're finding an LCD. Okay. Now, the reason for that is because we want to use the LCD to help us with some of these equations, okay? Some of these equations have fractions in them and look like these, okay? It might be easier to try to get rid of these fractions as quick as possible, okay? So what I want to do, that first one's kind of a generic one. The denominators are all 11 there, right? So the LCD that we're going to use is actually 11, okay? Because if I go through and I factor 11, 11 is 1 times 11, and then each one of those is going to have that, so 11 is the only factor that's needed there. Does that make sense? So it's kind of a trivial one. But the process then is, okay, well, if I multiply the left-hand side by 11, and then when I do the left-hand side, I should do the right-hand side, so multiply the right-hand side by 11, we should be able to get some fractions to disappear. Now, the only thing that you got to pay attention to here then is that if I'm going to multiply both sides by 11 here, I have to understand what I'm actually introducing. When I multiply this side by 11, and then multiply this side by 11, over here, what does this look like now? I have a number on the outside, and I got two numbers on the inside of these parentheses. It looks like the distributive property, right? So I have to be able to recognize that and realize that that's what I'm doing here. So now I'm going to distribute here, okay? And when I do this, and a lot of people are going to write this initially. If I go 11 times b, that's 11b, and then 1 times 11, right? So 11b over 11. When I distribute here, it's 11 times the negative 9, so it gives me negative 99, and then my b, and then 1 times 11. And over here, I'm just going to write it as 32 times 11 over 11. Okay, if you want to multiply that out and then divide by 11, that's fine, but we'll see why we want to do that here in a moment. What is 11 divided by 11 going to give me? That's 1. So that simplifies to 1b. What's 99 divided by 11 going to give me? 9. So it goes to the minus 9b. And now here, if I multiply that out, I could do that, but isn't that 11 over 11 going to be that factor of 1 that cancels out? And I'm left with 32. Okay? Do you see then, if I multiplied by 11 there, all that happened was I was left with the numerators, okay, the operations that kind of stick those numerators together, but I got rid of all my fractions, right? And then we can solve that equation. Does that make sense? So when you have fractions in your equation, guys, if you can recognize what to multiply by, a convenient value to multiply everything by, it's going to be beneficial, okay? Now, what a lot of people will do is they'll just put like and this is, I do this in my classes that are beyond this, so like my college algebra classes. So their third year of algebra, so they understand this, they've seen this. Basically what I do is I do this. I'll put 11 there, 11 there, and 11 there. I want to multiply every one of these fractions by 11 because that's what the distributive property basically said, right? And then I see, well, that 11's in the numerator, that one's in the denominator, they're going to cancel. And I'm left with just that b. Does that make sense? Here, that 11 up top, that 11 on the bottom, they're going to cancel. I'm left with just that negative 9b right there. And then these are going to cancel. I'm left with just the 32. Does that make sense? Okay. So then when we get to this next question, myself a little bit more room again. Looking at this question, I want to figure out the LCD. So I look at the factors of 3. 6 is going to go to 3 times 2, right? And the 3 is just 3 times 1, or 3. So as I'm trying to decide an LCD, I'm going off my directions prior. We're going to start with every factor that is inside each denominator. So 3 needs to be part of my LCD. Does that make sense? I'm going to go to the next in the 3 times 2. Well, when I look at that 3 times 2, I don't need to include this 3 because it's already here. Does that make sense? I've already used it once. So I don't need it. So 3 is going to be part of my LCD. So a lot of times what I do, like to the side, I'll just say LCD equals, and I know I got to use that 3. I'm not going to use that 3 because it's already taken care of here. But is that 2 new? So I need to carry over the 2. And then I look at this 3. Is that 3 new? Have I already used the 3 inside my LCD? Yeah. So I don't need that 3. Okay? So my LCD, if I multiply 3 times 2, gives me 6. And that tells me then that number that I can make all my fractions denominators grow to through multiplication. Okay? Kind of obvious that we can make all of those get to 6. Okay? So I'm going to multiply by 6. So I'm going to multiply this one by 6, this one by 6, and that one by 6. So now when I do this, I'll have 6n over 3, right? What's that 6 and 3 going to do? They're going to divide and give you 2. So I really got 2 times n then. What's going to happen? So here I'll get 30n over 6, but what is that 6 up top and that 6 on the bottom really going to do? They're going to divide out. And now I'm left with just 1 here times this 5n, so it's minus 5n. And now I'll have 6 over 3, but what's that 6 and that 3 really going to do? They're going to divide and leave me a 2, right? So now I got 2 times my 1. And now would you guys make the argument, would you agree with me, that if I started with this equation right here, and I asked you to solve that, or I asked you to solve this one, which one would you rather solve? You'd rather solve the bottom one. Okay? So one step of multiplication can get you to that point where you can do that. Okay? So then we can solve, ultimately when we do that, we get down to, one of these questions we're dealing with in 2.3 and 2.4. Okay? Now look at this one. Okay? Looking at my LCD, okay, this 4 is 2 squared. That's 2 times 2, right? Okay? Now when we do an LCD, if you've got repetitive multiplication, you want to write it as an exponent. So this 2 times 2 should be written as 2 squared. And this 5 is just 5, right? Does that make sense? So when I go through and try to figure out my LCD, I need that 2, but I need to take the exponent with it. Okay? I always choose the one that has the highest exponent. So 2 squared. And then I go to this denominator, that's a 5. So that needs to be part of my LCD as well as a factor. So I get 4 times 5, which ends up being 20. So my LCD, and hopefully you can visualize this with 4 or 5, and ultimately, this has got a 1 with it, right? Hopefully you can see that, yeah, if I were to start increasing 4 through multiplication and increasing 5 through multiplication, the first time that they become the same number would be when they're both 20, right? Okay? So then we multiply each one of these by 20. And now if I take 20 divided by 4, that's what's going on here, right? Those are going to cancel and leave you 5. So I have 5 times b. Multiply this 20 times 1/5. What's that 20 and that 5 going to do? Cancel and leave you 4, right? So then I got plus 4. And now 17 times 20 is going to give me 340. I can subtract 4 then. Oh, gives me 336. And then b will end up being 336 over 5. Subtract 4, yes. Huh? I subtract 4 from both sides. These are not like terms here. So I'm not subtracting the 4 from the 5. I'm just moving, I'm trying to get that over there with the other constant of 340. So I got to subtract 4 from both sides. Does that kind of make sense? Okay. At any time that you need a common denominator, okay, we try to use the least common denominator, but it doesn't matter what you use as long as it's a common denominator. So going back to this, okay, we chose 720 because that was the least common denominator. But if I keep going through here, I see one that's 1440. I'm going to kind of extend this pattern. And we should see that eventually in this list, I do get a 1440. Does that make sense? Okay. So 1440 is a number that I can make 20 and 144 both grow to through multiplication. Okay. Ultimately, I need to take 20 and multiply it by, 72? And that will give me 1440. If I take 144 and multiply it by 10, that will give me 1440. But that's another situation in which I can get those numbers to grow to the same number. Okay? So that would be a common denominator. Does that make sense? But 720 was least. It was smaller than that. It was the least common denominator. And that's the one we want to choose because it's going to make our math a little bit easier. But if you wanted to multiply by 1440, you could. Okay? So if I gave you the equation like this, let's go x over 2 plus, let's go 3x over 8 equals, and let's go 1 over 12. Okay? And we start thinking, okay, what can I make all of those grow to? Can I make 2 grow to 8? Yeah, but 12 won't grow to 8, right? It would have to shrink. So I got to make these. Can I make 2 grow to 12? Yeah, but can I make 8 grow to 12? No. Okay? And when I say grow, we're meaning growing by multiplication by a whole number. So I want to multiply by 1 or 2 or 3. If I take 8 and multiply it by 3 halves, it does grow to 8. 3 halves is not, or it grows to 12. 3 halves is not a whole number, though. Can we all maybe visualize that if I can make them all go to 24? Does that make sense? If I multiply 2 by 12, it goes to 24. 8 by 3 goes to 24. 12 by 2 will go to 24, right? So I can make them all grow to 24. Now, if you can't realize that, you don't see that right away, factor them. This one's going to factor to 2. This one's going to be 2 times 2 times 2, okay, which is 2 to the what power? 2 to the third. And then this one is going to go 2 times 2 times 3, right? What's 2 times 2 the same as, though? 2 squared, right? Just going to write it that way. So now as I go through and try to figure out my LCD, I know I've got to use 2. But 2 shows up several times, right? Which one of those do I really use? Do I use 2 to the first, 2 to the second, or 2 to the third? We use the one with the greatest power, so 2 to the third. Okay? The reason we choose the one with the greatest power is because if I use 2 to the third, it takes care of having a factor of 2. If I use 2 to the third, it takes care of having a factor of 4. Okay? So I know 2 to the third now. If I go through the rest, 3 needs to be incorporated too, right? So 2 times 2 times 2 is 8, times 3 is 24. Does that make sense? Okay? So there's my LCD. Multiply everything in here by 24 then. And if I do that 24 over 2, what's that going to give me? That'll give me my 12, right? So I got 12 x's. Okay. Here, 24 and 8 are going to divide to give me 3, right? So now I got 3 times 3, which is 9 x's. And over here, 24 and 12 are going to give me 2. So we got 2 times 1 then. Leaves me 2. That's a much simpler looking equation to start with than what I provided at the beginning, right? And that's the idea. We got to be able to find that LCD. Now, you could have multiplied by 48. You could have multiplied by 48. And what would happen there, because all those, the 2, the 8, and the 12, they can all grow to 48. They can all grow to 96 if we wanted to, okay? But if I multiply everything by 48, it's going to give me 24x plus 18x equals 4. It'll actually double that set of coefficients that I got. Does that make sense? But the answer will still be the same. All right, because everything doubled. Does that make sense? Yes. Another way, we talked about this in the last class, and this is the thing that I like about math, that there's a lot of different ways of kind of visualizing this stuff, but ultimately it's the same, okay? We've got x over 2 here, plus 3x over 8 equals 1 over 12. If I gave you a fraction like 2/3, what can I multiply that by so it gives me a whole amount? If I multiply by 3, will that turn it into 6 over 3, which is now 2? If I have 1 over 8, what can I multiply so I can get a whole amount? Multiply by 8, right? Won't that give me 8 over 8 then, which is just 1? If I have, give me two numbers. 7, and what's another one? 14. If I multiply by 14, will that give me 7? If I take a fraction and multiply by a fraction's denominator, it will give me ultimately the numerator, right? That's what we're seeing there. So let's do that. Let's say I want to get rid of this fraction. I'll multiply by 2, right? Now here's the thing. It's an equation. So I can't just change one thing. I got to change everything. So I'll multiply that by 2. That's fine. Those are going to cancel, leaving me 1x, right? But now I need to come over here and multiply by 2. Well, when I do that, I'm going to get 6x over 8. Does that make sense to everybody? Okay. And I come here and multiply by 2. Well, that's going to give me 2 over 12. So it's a little bit better because now I've only got 2 fractions instead of 3. What can I multiply everything by now to get rid of that 8? Multiply that one by 8. Multiply that one by 8. Multiply that one by 8, right? So that's going to give me 8x. Those are going to cancel. So now plus 6x equals now, this is going to give me 16 over 12, right? Does that make sense? Now, what can I multiply everything by to get rid of that 12? Multiply by 12, right? Multiply by 12, multiply by 12, that would give me 16. Multiply by 12, that's going to give me 72. Multiply this by 12, that's going to give me, what, 96? That equation is ultimately the same as that one. Okay? Because can I take and divide each one of the... No, it's zoomed out pretty far here. Let me grab this one. Control C. Control V. There we go. So those two equations, if we were to solve them, will end up giving me the same x. You see how if I multiply that by 8, it gives me this number here? If I multiply that by 8, does it give me that number there? If I multiply that by 8, does it give me this right here? Do you see how this one is 8 times big? Everything is 8 times bigger? So what that means to me then is that when I go through and solve, I'll still get the same x in either one of those. Okay? Because every part is 8 times bigger. All right? So if you want to do it that way, that's fine. That's multiplying by not the least common denominator, because ultimately what we multiplied by was a 2, and then an 8, and then a 12, right? So whatever 2 times 12 times 8, 2 times 12 times 8, 2 times 12 times 8. Calculator isn't working. 24 times 8, 192. So we all effectively multiplied by 192, which is not the least common denominator. The least common denominator was 24, right? Okay. But 192 is a multiple of 24, so we're fine. It works. Okay. That kind of makes sense on how to get rid of fractions? We'll continue to work on them. We'll continue to see them, and we'll use that process throughout the entire year. You'll use it all next year. Use it all the following year. Okay. But the sooner that we can realize that and kind of master that, it's going to make your life a lot easier when you see fractions. We all hate fractions, right? So if we hate something, we'd like to get rid of it as soon as possible, right? My daughter hates eating green beans. So when I give her a plate of food, she eats the green beans first. Get rid of them. Get rid of them as fast as she can, right? Okay? So if we see fractions, let's get rid of them as fast as we can. So multiply everything by an LCD, and we're good to go. And then we get a normal equation that we maybe still don't enjoy, but prefer over an equation that has fractions in it. So that being said, let's work on a couple examples from yesterday. We didn't get to. So this is from your worksheet from yesterday. Which one? The last one? Okay. So that last one, we've got a lot of things to do, right? Okay, left-hand side's messy looking, right-hand side's messy looking. Let's go ahead and do, we call this the implied algebra. Okay, when I say implied, we're kind of hiding what we want to be done there, right? What is supposed to be done right there? What's that telling me, Lindsay? Distribute, okay? So I want to distribute, so I need to multiply that 7 through. So what's 7 times 6? And what's 7 times negative 2? Okay. Now, when I look over here on this side, do I have a similar thing going on? So I need to take that 5 and get negative 15a. And take my 5 times the 1, and I get plus 5, right? Okay. Yes.
So,
yes.
I always get lost, like factor add.
Okay. So because they're on separate sides. Okay. So the first thing we would do is we would look to see we just kind of focus on one side first. Because this will be an issue eventually. I'm just going to look at just that yellow stuff. And I'm going to say, are there any like terms? Okay? So if there were any like terms, so let me just kind of add something here. What if I had like a 12a over here? Okay? Now if I'm looking at that side, now I'm going to do the 12a minus 14a. Does that make sense? Because they're on the same side. If they're on the same side, you do what's being told to you in that kind of expression. Does that make sense? Okay. So now, because there was nothing over there, I'm going to kind of skip that step. I don't have to combine any like terms there. On the right-hand side, okay, so we're looking at that. There are no like terms over there either, right? Okay. So there's nothing that needs to be combined there. So now the question is, what is our overall goal? If you remember, our overall goal is to get something of the form where we have an equation that says we've got variables on one side equal to constants on the other side. Okay? So we need to get all our variable terms to one side. And it doesn't matter which ones you move. Okay? So I'm going to look at this negative 15a. And basically what I want to do is I want to take that negative 15a and I want to get it over there. Okay? But I can't just move it over there the way it is. Does that make sense? We can't just cut and paste it and put it on the left-hand side. Because we want to make sure that we keep a balanced equation, right? If I put that negative 50, if I just cut and pasted it and did something like this, put like negative 15a over here, and got rid of that. Now my scale, okay, remember our scale kind of looking, kind of draw one here. Now my scale would be so much heavier on this side than it is on this side because I took that amount and it was negative, I put it over here. Does that make sense? Okay? What I need to do in order to keep that scale balanced is I need to add 15a here and add 15a there. So if you're going to work with both sides of the equation kind of at the same time to get all our variables to the left or all our variables to the right, you're going to do the opposite of what the operation is. So it was minus 15a, so now I'm going to add 15a. Does that make sense? So now, when I do that, I get 42. Negative 14a plus 15a is just 1a, right? Equal to, now this is the reason I did that. That now goes to 0, right? Is equal to 5. It's a completely new looking equation, but because I added the same amount to both sides, I started with that balanced scale, and then I put the same amount on both plates of that scale, so it's still balanced. Does that make sense? So this is still a true statement. Now, do we have our variables on one side? Here we had variables on both sides, right? Now we've got variables on one side. So let's leave that variable there. Let's leave that positive a there. How am I going to get that 42 to the other side? Okay. So you can do that. If I subtract 5 from both sides, I'm going to get 37 plus a equals 0, right? And now what would you do? Say again? Well, are they like terms? To be like terms, you have the same variable, right? So remember, we want to try to get these separated. Because we want variables on the left, we want constants on the right. Can I take this and get it over there? And when I'm going to get it over there, is I want to make how do I make 37 turn into 0? Subtract 37. Subtract 37. That's going to go to 0, right? And you have now 0 plus a, which is just a. And what's 0 minus 37? Negative 37. Now, that's fine, and you can do that. But if we've got to be a quicker way to erase things. If we've got this situation going on right here, and we've said we were trying to separate the variables and constants, we want to leave that variable where it's at. Okay? This is a constant, right? Let's get that separated. Let's get that moved away. So in order to move that away, I'm going to subtract 42 here. Does that make sense? Subtracting 42 is going to make that go to 0 plus a, which is just a. And now come over here and subtract 42. What's 5 minus 42? Negative 37. Same answer though, right? So if you want to do it your way, where you subtracted 5 from both sides, that's fine. As long as you do the same thing from both sides. But then the last step then is to remind ourselves that we need the variables and constants to separate. We need one on the left-hand side, and we need the other one on the right-hand side. So then you got to do that operation to conduct that, to get that finished. Okay? I'm going to give you guys a minute to, I had them here. Let's see, zoom out real quick. There we go. Take a minute and see what we come up with on that one.